Hello everybody, welcome back, I'm Vinny, and this time I'll finally talk about behavior trees. Behavior trees are used to create complex AI by using small, independent tasks. Every behavior tree has a root node that's just a simple node that's the entry point of the tree. Then there are leaf nodes, which is where our custom logic lives, where we implement your actions and conditions. The composites are the brains of your tree. Composite nodes are also known as control flow nodes because this is what they do. The two most common implementations are sequencers and selectors. A sequencer expects all its children to succeed, so it executes them in order, and in case one fails, it does not execute the remaining ones. The selector node does the opposite. It requires only one child to succeed. So it also executes their children one by one and stops as soon one succeeds. The last type of nodes you should know about are decorators. I don't think they are really included in the mathematical definition, but it's a common type of node in game development. It helps to make the tree less complex and the nodes more reusable. So here are some examples of decorators. The inverter, also known as NOT, is a node that inverts the output of its children. The succeeder, or always succeed, returns success regardless of the result. And the limiter works slightly different from the other ones. Instead of changing the output, it adds a limit on how many times its children should be called. Now that you have a high-level idea, let's jump to the code. I've created this project to show a behavior tree in action. One thing I didn't mention is that nodes in a behavior tree will return one of these three states: success, failure, or running. The naming may change slightly depending on the implementation, but the meaning is always the same. Nodes will also have a common method. In here it's called tick, but you can see it as process or update in other implementations. This is the method called by the parent node. Regardless of name, it always receives two arguments, an actor and a blackboard. The actor is the element which the behavior tree is applied to, and the blackboard is the object where your nodes can store or share data. This is basically the interface of every node in a behavior tree. So in this example, I have two nodes that I call home, like they are part of the group home. What I want in this example, I want the NPC to follow my mouse. And currently it's not doing anything, so it's going to try to follow my mouse, but if my mouse is too far from the NPC, I want it to go home. And because there are two homes, I want it to go to the closest home. So I'm going to show you how a behavior tree for this NPC would look like. Now that you know the basics, let's start creating the behavior tree. I first add the root node and selector as first node. Now I will add the sequencer. I'll start by creating the action node that moves the actor to the mouse position. I'll start by creating the simplest solution first, and as I implement new scenarios, I'll refactor it to make it more generic and reusable. After adding the action node, I need to come to the inspector here in the script field and select the option Extend Script. This creates a new script extending my action node. Now I need to implement the tick function. Get the mouse position, and makes the actor move in its direction. If I run my example, you can see my NPC is already following the cursor. Another thing I need to include here is that when you have an action that takes more than one tick to complete, you should return running as a state. Here I'll check if the distance is less than 1 pixel, just to make sure I don't get some weirdness with rounding issues. If it is, I consider the task as completed. Otherwise, I return running. Now that my actor is following the mouse, I need to add a condition to stop in case the mouse is too far. For this, I create a condition node. That's virtually the same as the action node, but with a different icon. My condition will check if the distance to the mouse position is less than, let's say, 300 pixels. Now, when I execute my scene, you can see that the NPC only follows the mouse when it's close enough. However, you shouldn't have values hard-coded in your nodes. To take rid of it, I'll define a parameter called detection radius, so when reusing this node, I can define a different value if I wish. Godot exposed these parameters as a field in the editor, which is quite handy. Let me set 600 pixels here. Now you can see the nodes following the mouse from farther. Let me now implement the second branch, which is go to closest home. I'll add a sequencer for that under my main selector. I'll create a simple implementation here at first and then refactor it. I'll create a new action, go to home position. First, I'll get all the home nodes. Then, I'll implement a logic to get the closest one. If it can't find any home, it fails, otherwise it moves the actor towards home. Let's see it working. As you can see, it tries to follow the cursor, but when it's too far, it goes to the closest box. Now let's make it better. There are a few things to improve. First of all, this action is doing too much. So we are going to break it in smaller tasks. I'll move this find home logic to another action and save it into the blackboard. The go to home position action now just needs to retrieve the position from the blackboard and use it. You can see it still works. Now you may notice that go to home position and go to mouse position are quite similar. So let's make it more generic so we can use the same script. One good practice is to never hardcode blackboard keys inside the nodes, as it makes it less reusable. So let's change it. So I moved the key name to the field in the editor, and I also rename some variables here. Now you can see this script is quite generic, so I can rename it from go to home position to go to target position. Now I'll also move the blackboard key from the find closest home. And another improvement would be moving the group name to a parameter. So this way, this action node now is not about finding the closest home anymore, but finding the closest member in a group. One thing you may have noticed is that the name of the nodes and the name of the scripts being used are not the same. And that's totally fine, because I want my scripts to be as generic as possible, while my nodes should be descriptive enough so I know what my behavior tree is doing. The last thing I need to change to be able to use my generic go-to-target script in my go-to-mouse node is to move the logic that captures the mouse position. This logic is actually used in two places, so I'll end killing two birds with one stone here. I'll call my new action load mouse position, and it will get the position and save to the blackboard. Now I can get it from the blackboard in the script that checks if the mouse position is nearby, and it becomes generic enough that I can even rename it to isTargetNearby. And now my go-to-mouse-position node script can be replaced by the generic one. And I just need to define my mouse position key from the blackboard in the parameter. Let's check if it still works. Perfect. Now let me show you the power of reusability in behavior trees. Let's add another action to my tree. Let's say if the NPC reads home, it changes its color. This is the third branch in my main selector. The way the tree is working right now, this node will never be called, as you can see here. The reason for that is that the branch to move to home position is always called, even if the items are at home. So my selector always resolves to the second option and never tries the third one. To fix that, I need to add a condition node that checks if the item is already at home. Luckily, I can reuse the script isTargetNearby. I just need to set the detection radius to 1, which means both NPC and home are technically in the same position. However, this script succeeds when the item is nearby, and what I want here is the opposite of that. I want it to fail in case the item is too close. For that, I can use an inverter decorator. Now it's following the mouse. If the cursor is too far, it tries to go home, and if it reaches home, it changes its color to red. That's it. So besides implementing the change color logic, I didn't have to implement a single line of code extra to make this validation. And that's the cool thing about behavior trees. Once you have your basic nodes implemented, you can reuse them as you wish. So this is how our behavior tree looks. In the first sequencer, it tries to follow the mouse. It loads the mouse position, checks if the mouse is nearby, and then go to mouse position. In case this one fails, it tries the second sequencer, where it finds the closest home, checks if the item is already home, and in case it's not, it goes to home position. So if this one also fails, it tries the third option, that's just changing the color. We could reorganize this tree in a different way. The first part that follows the mouse would remain the same. The second sequencer would check the items at home, and if so, it would change its color. And in case this one fails, it tries to go home. Either way, both trees would do the same thing. So that's it what I have for this video. I hope you enjoyed. Until next time.